Week we're talking about artificial intelligence. Most of the lecture will come out of a book called The Myth of Artificial Intelligence by Eric Larson. And wait a minute. There we go. Okay. And there's a reference, Harvard University Press. E.J. Larson, 2021, The Myth of Artificial Intelligence, Why Computers Can't Think the Way That We Do. And that's what the book actually looks like. The story of artificial intelligence starts with computer pioneer Alan Turing, who published a paper on the topic in 1950. Turing proposed to test a computer's intelligence by having a computer and human perform the same task. The task will then be judged by a group of judges, and if the majority of the judges can accurately identify which is the computer and which is the human, the computer wins. This is known as the Turing test. He came up with it in 1950. A computer, an artificial intelligence has never ever won. They win in singular things. They have developed computers that could play chess. They've developed computers that can play a Chinese game called Go, which is a very complex game. But the computer that plays Go cannot play chess, and the computer that plays chess cannot play Go. As weird as that is, we're going to talk about Watson. Watson was a computer program that was put together to win in Jeopardy, and it did. It won, but it couldn't do anything else. So, artificial intelligence. The human brain, of course, can do everything, can do anything, can think in 100 different directions at the same time. Computers can only think in one direction. During World War II, Bletchley Park England's most progressive thinkers came together to break the German and Japanese communication codes. Curiously enough, my aunt didn't work at Bletchley Park, but she worked in Washington, D.C., breaking the Japanese codes. And she is in a book. I just read the book called Code Girls, and she's in there, as curious as that is. And she used to tell us that she broke the Japanese code, or she worked on the Japanese code. This has all been secret for about or until the 1980s. But my aunt worked on Japanese codes. Guessing is known in science as forming hypotheses, and it is absolutely fundamental to the advancement of human knowledge. The Bletchley effort amounted to a system of guessing well. So what they were doing, they were putting together the codes. They were translating them using their best guess, and for the most part, they were right. Intelligence is situational. There is no such thing as general intelligence. Your brain is one piece in a broader system, which includes your body, your environment, other humans, and culture as a whole. Intelligence is contextual. Far from existing in a vacuum, any individual intelligence will always be both defined and limited by its environment. Human intelligence is largely externalized, contained not in your brain, but in your civilization. And no one knows that better than a Dene person. Your culture you are wrapped up in your culture is wrapped up in you. Your brains are modules in a cognitive system much larger than itself. Now, this is really kind of an interesting book because a lot of it is philosophical, some of it's physics, has to do with intelligence and defining intelligence. How do we define intelligence? If a computer can answer all of the questions that you can find, is it intelligent? And the answer is probably not, because that's all it can do. It can only answer the questions that it has been programmed to answer. It can't create new knowledge. And that's the difference between your brain and artificial intelligence. Artificial intelligence can only do what it's been programmed to do. Therefore, it can only have the answers that have already been created. It can't create its own answers. Can intuition be programmed? The idea of programming intuition ignores a fundamental fact that are about our own smarts. Humans have social intelligence. We have emotional intelligence. We use our minds other than to solve problems and puzzles, and that's of course what computers are made to do. They don't understand. There's lots of things they don't understand. They don't understand humor. They don't understand sarcasm. They don't have social intelligence. They don't have emotional intelligence. All they can do is solve puzzles. The problem-solving view of intelligence helps explain the production of invariably narrow applications of artificial intelligence throughout its history. Game playing has been a source of constant inspiration for the development of advanced artificial intelligence techniques. But games are simplifications of life that reward simplified views of intelligence. A chess program plays chess, but does rather poorly when driving a car. And of course, we have had difficulties with self-driving cars at this point. There have been a number of accidents, no deaths yet, but there have been a number of accidents. Treating intelligence as problem solving gives us a narrow application. If machines could learn to become general, we would witness a smooth transition from specific applications to general thinking beings. We would have artificial intelligence. To accomplish their goals, what are now called machine learning systems must each learn something specific. Researchers call this giving machines a bias. The bias has to do with what it can do. As we see this computer playing chess, that's all it can do. It can't drive a car. It can't play in any other game. It can't answer questions on Jeopardy. All it can do is play chess. Researchers have realized that giving a machine learning system a bias to learn a particular application or task means that it will do more poorly on other tasks. There is an inverse correlation between a machine's success in learning some one thing and its success in learning some other things. Machine learning bias is typically understood as a source of learning error, a technical problem. Machine learning bias can introduce error simply because the system doesn't look for certain solutions in the first place. But bias is actually necessary in machine learning. It's part of learning itself. And of course, the other problem that we have with artificial intelligence is the question, who's doing the programming? Is it an individual from Stanford University? Is it an individual from Mumbai, India? Is it somebody from Jakarta in Indonesia? Is it somebody from Berlin? Is it somebody from Moscow? Is it somebody from Scandinavia, from Stockholm? This will change the answers that it comes up with. And for that reason, and this is one of the reasons that I have argued against ChatGPT. There aren't any Dene people that are programming these computers. So how in the world could it possibly write like you would write? How could it possibly say what you would say? You have a specific civilization. You have a specific culture. So how can ChatGPT come up with the same answers that you would come up with? Things occur to us. We reason through our observations and what we already know. Answers pop into our heads. All of this buzz of biological magic remains opaque. It's processing. It's still uncharted. It's the magic of the biological magic of the human brain. Things pop in, ideas pop into our head. I take an hour-long walk every morning in nature, and things just pop into my head as I'm walking. Ideas come to me. If I were a computer, it couldn't do that because I could only think in one direction at a time. Machines tasked with designing new and better machines face a fundamental stumbling block. Any design for a new machine must be specified in the parent machine. The parent machine would necessarily be more complex, not less, than its creation. An organization which synthesizes something is necessarily more complicated, of a higher order than the organization that it synthesizes. In other words, the machine that makes the other machines has to be more complex than the machine that they're making. The machine that they're making can't possibly be any smarter. They can't make a new machine that's smarter than they are. For example, if we've got a machine that has an IQ of 160, it can only make another machine that has an IQ of 160. That's the best it can do. It can't make one that's has an IQ of 180. It can only make a machine that has either 160 or less IQ. Inference is to bring about a new thought, which in logic amounts to drawing a conclusion and more generally involves using what we already know and what we see or observe to update prior beliefs. Inference is a basic cognitive act for intelligent minds. If an artificial intelligence system is not inferring at all, it doesn't really deserve to be called artificial intelligence. We know a lot of things, but only inference gets us to new knowledge. Real-world circumstances are always changing, so real-world inference is common and necessary. And this is part of our problem with artificial intelligence. They can't infer. The ability to determine which bits of knowledge are relevant is not a computational skill. Human insights are not arrived at by formula. Scientists frame hypotheses, then test them, but the hypotheses aren't arrived at mechanically. They sometimes just pop into scientists' heads, typically after mastery of the field. Then they have the idea. That's where they come up with their hypotheses. Copernicus posited that the Earth revolved around the sun. He made it a conjecture that went against all previous knowledge. The fact that conjectures lead to discoveries doesn't fit with mechanical accounts of science. It contradicts them. But detective work, scientific discovery, innovation, and common sense are all workings of the mind. They are inferences that artificial intelligence scientists in search of generally intelligent machines must somehow account for. Conjecture. Machines can't do it. Deductive reasoning is a logical approach where you progress from general ideas to specific conclusions. The problem with deductive reasoning is that it never adds knowledge. Deduction is useless in the pursuit of knowledge, and it only clears up disputed beliefs if bona fide errors in reasoning are made. Conspiracy theorists might never make deductive reasoning mistakes. It's just that they adopt premises as true that others find dubious or just crazy. And of course, that's what deductive reasoning is, taking two known facts and creating a third fact. All dolphins are, and this is an example of deductive reasoning. All dolphins are mammals. All mammals have kidneys. All dolphins have kidneys, and that's deductive reasoning. But this is all knowledge that we already have. They're not creating new knowledge. They're just stating knowledge that is already there. Induction means acquiring knowledge from experience. Induction captures the everyday idea that we gain the ability to explain and predict by observing happenings in the world. Modern artificial intelligence is based on statistical analysis and so relies on an inductive framework. which is useful for many commercial applications. Artificial intelligence can offer recommendations, a type of prediction based on past observations. At its root, all inductions are based on enumeration, but it can't create new knowledge. Machine learning can never supply real understanding because the analysis of data does not bridge to knowledge of the causal structure of the real world, essential for intelligence. The ladder of causation steps up from associating data points, seeing and observing, to intervening in the world, doing, which requires knowledge of causes. Then it moves to counterfactual thinking, like imagining, understanding, and asking, what if I had done something different? Causal structure in the real world. Common sense is what enables two people to engage in ordinary conversation. The problem of common sense, and in particular language understanding, which requires it, has been a signal concern among artificial intelligence researchers since the field's inception. Machine learning is getting computers to improve their performance based on experience. There are two types of learning: supervised learning and unsupervised learning. Supervised learning is identifying information that leads to a desired outcome. In other words, that's what most computers do. They have supervised learning. They only have one path that they can take. And unsupervised learning, where masses of data is analyzed to determine patterns of information. Early artificial intelligence scientists assumed many problems in the real world could be solved by supplying rules amounting to functions with known outputs, as with addition. It turned out that most problems that count as interesting to artificial intelligence researchers have unknown functions. Hence, we now have machine learning, which seeks to approximate or simulate these unknowns. This fakeness of machine learning goes unnoticed when system performance is notably close to a human's or better. But the simulative nature of machine learning gets exposed quickly when the real world departs from the learned simulation. So as long as it's simulation, we're okay. But as soon as we put in the real world aspects, the real world factors, the artificial intelligence cannot come up with solutions. The limits of a machine learning system's world are precisely established by the data set given to it in training. Any given data set is only a very small time slice, representing partial evidence of the behavior of real-world systems. A trained system can predict outcomes, seemingly understanding a problem until an unexpected change or event renders the simulation worthless. Simulations that fail can be worse than worthless, as with a robot car or an automated prediction that instills false confidence. And that's part of the problem with artificial intelligence, is the idea that we know that these are right. Sometimes GPS leads us the wrong way. That's happened to my wife several times. She was going to North Carolina, and she should have driven to Indianapolis and then gone south, gone through eastern Tennessee. And when she hit the mountains, when she hit Chattanooga, she should have turned left. But what it did instead, it took her through Indiana, then it took her through Ohio, dropped her down into West Virginia, and forced her to go through Virginia and then to North Carolina. She went to Asheville. She was headed to Charlotte, North Carolina. And it took her a much longer than it would have had she gone the way logic would have told her to go. But she likes to follow. She likes to let the computer tell her how to get there. And it took her a couple hours longer. So GPS sometimes makes mistakes. Computers sometimes make mistakes. The problem is computers think in such absolute terms that they don't know they made mistakes and they assume everything that they do is correct. Computers are the same way. Some people are the same way. Most of us can admit when we've made a mistake, however. The most powerful learning systems are much more narrow and brittle than we might suppose because the systems are just simulations. All the problems of induction bedevil machine learning and data-centric approaches to artificial intelligence. Data are just approved facts stored in computers for accessibility. And observed facts don't get us to general understanding or intelligence. It just can't do it. They are simulations. And the reason they're simulations is because that's the way computers are set up. If this, if it's deductive reasoning. You're asking me this question, this is the answer to that question, therefore this is the outcome. It's a simulation. It's always the same thing. If you ask it this question, you always get this answer. It can't think in two different directions at the same time. My son is a math whiz. He's really good. And he was teaching mathematics in Florida and then in North Carolina. He's teaching high school students. And one of the problems that he had, or one of the problems that the math department had, was the people teaching math were education majors. They weren't math majors. So when they looked at a problem, there was only one answer to the problem. There was only one way to do the problem because they were not math majors. They followed the book. They always followed the book. There's only one answer to every question. There's only one way to do it. That's the way the computer told them to do it. That's the way the book told them to do it. So that's what they did. My son, on the other hand, since he studied mathematics and he understood that there's a lot of different ways to get to the same answer, could look at a problem and he could see two or three different ways to do it. And so he showed the students that, because some students think differently think in different ways than others. Some people are visual learners, some people are oral learners, some people are tactile learners. And since there are so many different ways of seeing things, if you're human, then he was able to come up with a lot of different answers. But a computer can only come up with one answer and only one way to do it, because it's 1, 2, 1, 2, 1, 2, 1, 2. It's either a 1 or a 0, actually, is what it is. There are no 2s. Anyway, big data is an inevitable consequence as computers become more powerful, statistical techniques like machine learning become better, and new business models emerge, all from data and its analysis. What we now refer to as data science is really an old field given new wings and massive volumes of data, mostly made available by the growth of the web. Big data into artificial intelligence. The focus on deep learning makes sense. The algorithms, rather than the data, are responsible for trouncing human champions at Go, mastering Atari games, driving cars, and the rest of the artificial intelligence successes. Big data has found a home in artificial intelligence, as data-driven approaches like machine learning all benefit from huge volumes of data for training models and testing them. As one observer put it recently, big data, I'm sorry, I thought I corrected that. Big data has become big data artificial intelligence, bug data. Machine learning systems are sophisticated counting machines. The frequency assumption comes into play because the greater the frequency of hits on a feature, the more useful it is. Sarcasm is particularly opaque to machine learning, in part because it's less frequent than literal meaning. Counting turns out to work well for certain obvious tasks online, but works against more subtle ones. Sarcasm isn't a word-based feature, and neither is it as frequent as literal meaning. Machine learning is notoriously obtuse about such language phenomena. And of course, it can't read humor. It has a difficult time reading humor, and of course, it has a difficult time reading sarcasm as well. Saturation occurs when adding more data, more examples, to a learning algorithm or a statistical technique adds nothing to the performance of the system, and that's what we're seeing here. This is the optimum functioning of the algorithm, and as you can see, the more data you put in there, it really doesn't do any good. Usually it plateaus, but in this case it's going down. When we seek to understand particular facts rather than regularities, we are forced into a kind of conjuring, the selection or invention of a hypothesis that might explain the fact. Induction moves from facts to generalizations that give us knowledge of regularity. But abduction moves from observation of a particular fact to a rule of hypothesis that explains it. Abduction is tied closely to reasoning from events to their causes. And of course, humans can do that, but computers can't. Abduction captures the insight that much of everyday reasoning is a kind of detective work, where facts, data, as clues are seen to help make sense of things. Humans are extraordinarily good at hypothesizing, which is not explainable by mechanics, but by an operation described as instinct. Guessing from infinite possibilities, the most plausible hypothesis is selected. These factors must be included in developing artificial intelligence. Without an abductive step, inductions are blind and deductions are useless. And this is one of the reasons why artificial intelligence is nearly impossible, because it cannot abduct. It cannot look at an observation and come up with a hypothesis. It can only do what it's been told to do. So if this is new information, it can't deal with it because it doesn't have that information. If deduction is inadequate and induction is inadequate, then there must be a theory of abduction. Since there is no theory, it can be concluded that there is yet to be a path to artificial general intelligence. Causal information about the world cannot be extracted from associations in data, so explanations involving why or how questions can't even be formulated, let alone answered. Causal knowledge forms part of common sense understanding of the world and explains why data as effects or clues to prior causes that contribute to understanding can be seen. So you can't ask a computer why or how, because they can't come up with answers for why or how, unless they already have that information in their database. Imagination involves inferences that don't exist in a data set. Imagining requires conjecture, if anything does. Abduction is inference that sits in the center of all intelligence. And of course, computers can infer, they can't conjecture, and they certainly can't abduct. Most of what is known is implicit. Knowledge is brought into consciousness, making it explicit, only when circumstances require it, like when someone is surprised or has to think through something deliberately. All implicit knowledge might be necessary for some inference or other, but the total amount is vast. The knowledge base of an ordinary person is unbelievably large, and inputting and representing it in a computer is a gargantuan task. Abduction gets harder and harder. It soon departs from all known conceptions of automatic inference or computations. Take scientific discovery or innovation. Human beings invent languages, concepts, and laws to explain the world. This is creative abduction. Creative abductions leap to novel conceptual framework themselves. Mysterious and wonderful abduction inferences pervade human culture. They are largely what makes us human. All roads lead here. Artificial intelligence lacks a fundamental theory, a theory of abductive inference. The problem is that little of everyday world is captured by timeless truths, and even when there is certainty, deductive inference ignores considerations of relevance. Inductive inference provides provisional knowledge because the future might not resemble the past, as in this picture. That's a computer, that's a typewriter, this is a camera, this is your phone that you take pictures with now. So the future might not resemble the past. Intelligent thought involves knowledge that outstrips what can be bluntly observed, but it's a mystery how knowledge is acquired and how the right knowledge is applied to a problem at the right time. Neither deduction or induction illuminates this core mystery of human intelligence. The abductive inference that was proposed long ago does, but no one knows how to program it. We can't program abductive inference. We get a fatal error when we do. We've got three options: weep, weep, weep. In pragmatics, what is said is tightly dependent on how it is said and why it is said. What people mean is almost never a literal function of what the word for word say. This feature of ordinary talk, studied in linguistics as pragmatics, is what makes language interpretation hard for artificial intelligence, but meaningful, interesting, and generally easy and natural for people. A word phrase whose meaning can't be understood outside its cultural context. For example, Lisa's father worked long hours to bring home the bacon. Literal meaning is he actually brings home the bacon, and in the idiomatic language, it means that he works hard to make a living for his family. Prose showcases the ubiquity of pragmatic phenomena in language. In nearly every ordinary sentence, it's inescapable. Deixis refers to words like pronouns that cannot be understood or disambiguated without knowledge of context, like me or he or here. That's known as deixis. Deixis means pointing, and the language often points, and this is understood by the listener in context. So understanding who me is has to do with context. Understanding who he is has to do with context. Understanding where here is has to do with context. A system engaged in conversation, not resorting to canned tricks, must keep track of all of this. And of course, deixis is possible for humans to do. It's almost impossible for artificial intelligence to do. They just don't understand pronouns. In the early part of the 20th century, the philosopher of language Paul Grice offered maxims for successful conversation. The maxim of quantity: try to be as informative as possible and give as much information as is needed, but no more. That's the maxim of quantity. The maxim of quality: try to be truthful and don't give information that is false or that is not supported by evidence. The maxim of relation: try to be relevant and say things that are pertinent to the discussion. The maxim of manner: try to be as clear, as brief, and as orderly as you can, and avoid obscurity and ambiguity. Grice's maxims. In 2004 at IBM Research, the head researcher said, "We're going to make history. Money isn't an object. Find a way to build a system that plays Jeopardy." IBM assembled a team of top talent and spent the next 3 years doing due diligence on the requirements for a question answering system capable of playing world-class Jeopardy. They took 3 years to create a computer program that could win at Jeopardy. The magical quality of IBM's Watson system is its search for answers. Fully 95% of all answers to Jeopardy questions are just Wikipedia titles. Did you get that? They're Wikipedia titles, and that's how they taught it. They struggled for years trying to figure out how to program the computer to answer these questions. And then somebody came up with the understanding that almost all the answers are Wikipedia titles. In other words, if you look at Wikipedia, it's the title of the page. This serendipitous discovery made the entire effort possible. Simply matching questions to Wikipedia titles would by itself result in superhuman level gameplay. As usual, the devil is in the details, and these two guys evidently are the two highest earners on Jeopardy. Watson crushed Jeopardy, but had no other function. Watson proved once and for all that all successful AI is narrow. Artificial intelligence is narrow. I keep saying that. They can only do one thing. And in this case, Watson could only do one thing. It could only answer Jeopardy questions. Watson is not a step toward general intelligence, but rather further evidence that the quest for generality remains mired in mystery and confusion. While the IBM team did score an impressive victory using a powerful hybrid system, it did not discover a key to language understanding. All the problems of programming inductive inferences for general intelligence remains. It could only do one thing. And this is what a computer program looks like. It's either a 1 or a 0. It's either empty or it's got something in it. And that's how computer programs are created. It's a binary system. There's only two numbers. Binary means two numbers. The two numbers are yes and no, 0 and 1. Every reasoning machine has had two inherent impotencies. It is destitute of all originality and initiative. It cannot find its own problems. It cannot feed itself. It cannot direct itself between different possible procedures. The capacity of a machine has absolute limitations. It has been contrived to do a certain thing, and it can do nothing else. It can do one thing. That's its brilliance. In 2005, there was a blogger revolution to make the internet as free as possible. Web denizens were poised to rewrite the rule books, ridding the world of stodgy gatekeepers like mainstream press and media, who unfairly control the production and flow of news and knowledge. Power to the people was the trope of the mid-2000s, spread endlessly in blogs, commentary, in an online collaboration of hive mentality. Instead, the billionaires took over and made more money. Who are the billionaires we're talking about? We're talking about Bezos, we're talking about Bill Gates, and we're talking about Zuckerberg. The human brain has more than 100 trillion neuronal synapses, so a computer recording a simple binary piece of information about synapses would require 100 terabytes. The amount of storage needed to store even this simple information every second over the course of a day for one person would be more than 100,000 terabytes, or 100 petabytes. Supercomputers hold about 10 petabytes. So just this one little piece of information would take 10 supercomputers. This quick calculation doesn't account for the changes in connectivity and positioning of synapses over time. Counting how these connections change just after a good night's sleep or a class in mathematics amounts to a whopping figure that we cannot compute. Attempts have been made to promote inductive reasoning in computers while representing an advance in applying machine learning to biological data sets. The approach has an average error rate of 2 in 10. 2 in 10. This has ominous implications for any strategy for reverse engineering the human brain. It is the shallow logic behind such approaches that spell deeper trouble for the institution of science. So if we think that computers are going to be smarter than humans, we're sadly mistaken. They make too many mistakes. 2 in 10 error rate. Artificial intelligence and big data works only when we have prior theory. A great deal of confusion and potential trouble for science lies precisely with this point. Neuroscience, unlike particle physics, has no unifying theoretical framework. The challenge for neuroscientists is to defend the current data-driven model in the absence of theoretical insights, making sense of guiding the deluge of data. Society is about to experience an epidemic of false positives coming out of big data projects. When you have large amounts of data, your appetite for hypotheses tends to be even larger. If it's growing faster than the statistical strength of the data, then many of our influences are likely to be false. They are likely to be white noise. Remember, when we're talking about dealing with data, we have 2 out of 10 of our conclusions are false, are incorrect. The danger of outfitting theories, models to data, where outfitting here means spuriously matching a set of data points to a description that contains no genuine explanatory power. The description does not generalize to new unseen data points in the underlying distribution in question. It can't answer the questions because if any of the information is spurious and if any of it is inaccurate, then that messes up all the data. The simplest case of model of a set of data points is the linear interpolation of a scatter plot. A straight line shows the average interpolation of the scattered data, and as such gives a useful model predicting the behavior of the data. Overfitting, making the data fit the hypothesis, gives false confidence on existing data, but quickly shatters this illusion when new data arrives that doesn't fit the model or theory. New ideas can't be predicted, and thus we should expect the consolidation of the web into big tech with skew work on artificial intelligence toward narrow applications on the profit curve, while inventions that can never be counted on get short shrift. And that's the problem. Over the last year, magazines around the world have discussed the benefits and dangers of artificial intelligence technology. The May issue of the AARP Bulletin warns of grandparent scams, where artificial intelligence software synthesizes a grandchild's voice and creates a plea for quick cash in the child's synthesized voice taken from a social media post. And this is the bulletin that came out. I get it because I'm over 50, and it was an article written by Morris in 2023. I'll show you the reference at the end of this. The June issue of the APA's Monitor on Psychology suggested that psychology professors find a way to teach using ChatGPT, even vaguely suggesting that critical thinking could be supported by helping students think critically about topics they're already familiar with, like talking with a colleague. It can be an interactive partner. Huh? And that's in Monitor on Psychology. They're trying to tell us we should use it. And then they explain, well, this isn't going to work for most of your classes, but I'm doing, this one professor is doing one on intelligence and stupidity. That was the title of his class. He can use it. Even the Saturday Evening Post has weighed in on the debate of artificial intelligence and ChatGPT. Altman states that artificial intelligence has been helping us for decades with computer problems. Clippy, the creepy animated paperclip from an earlier version of Microsoft Word, hovered around and made faces while you typed. It was artificial intelligence. It has been observed that ChatGPT will pick up on negative societal biases. For instance, if an algorithm is trying to determine which job candidate is the best fit, it will look at what qualifications correlate with a successful employee. If the company hired mainly non-diverse people, the algorithm will continue to recommend non-diverse candidates. This can have dire consequences when all algorithms are assessing creditworthiness or for borrowers or recidivism rates for convicts, as well as suitability for employment. If AI knows everything about you, it can manipulate you in ways that will make targeted marketing look quaint. And the universe of fake news, the fakes are going to get a whole lot more realistic and difficult to challenge. Imagine the possibility of creating a fake video showing a politician mouthing words they've never actually spoken or participating in some shameful activity that never actually occurred. That's becoming easier than ever to do. As the saying goes, knowledge is power. Cynical opinion leaders and crooks will certainly use artificial intelligence to mislead and defraud. And this is from the July and August 2023 Monitor on Psychology. This is really kind of an interesting picture because I took this from an article that talks about putting celebrities' faces on pornography. And in this case, of course, they're changing the First Lady's face to Reese Witherspoon. So you can actually do that. Deep fakes, they call it. And of course, you can do that with any celebrity. They did that with, well, not pornography, with Harrison Ford in the new Indiana Jones movie. After the June issue of Monitor on Psychology tried to convince psychology professors to embrace the technology, don't get left behind, the July-August issue offered a different take on artificial intelligence. Artificial intelligence tools used in healthcare have discriminated against people based on their race and disability status. Rogue chatbots have spread misinformation, professed their love for users, and sexually harassed minors, which prompted leaders in tech and science to call a pause to research in March of 2023. What protection could help ensure privacy, transparency, and equity as these tools are increasingly used across society? Researchers analyzed interactions at a hotel in Malaysia, employing both robots and human workers. After hotel guests interacted with robot workers, they treated the human workers with less respect. There was a spillover effect where suddenly we have these agents that are tools, and they can cause us to view humans as tools too. In addition to making mental health support more affordable and accessible, bots can help people who may shy away from a human therapist, such as those new to therapy or people with social anxiety. They also offer the opportunity for the field to reimagine itself, to intentionally build culturally competent AIs that can make psychology more inclusive. My concern is that AI won't be inclusive at the end of the day. It has to be trained. And of course, the problem is who is programming it. And I've talked about this before. Who is programming the who's programming the artificial intelligence? Is it being done in San Francisco? Is it being done in China? Is it being done in India? Is it being done in Malaysia, Berlin, Paris, the Ukraine, in Turkey. Depending on who is programming it, that's the answers that it's going to come up with. In January, the mental health nonprofit COCO offered counseling to 4,000 people without telling them the support came from ChatGPT-3, which is a chatbot. Reports have also emerged that getting therapy from generative language models, which produce different text in each interaction, making it difficult to test for clinical validity or safety, has led to suicides and other harms. Before integrating artificial intelligence tools into their workflow, many clinicians want more information on how patient data are being handled and what apps are safe and ethical to use. The problem is, if we're putting this into an artificial intelligence, is somebody able to glean all that information? Is all this is any of this private? Can it possibly be private? The field also needs a better understanding of the error rates and types of errors those tools tend to make. Remember, 2 out of every 10 pieces of information are incorrect. Psychologists have long measured behavior through self-reports and lab experiments, but they can now use artificial intelligence to monitor things like social media activity, credit card spending, GPS data, and smartphone metrics. That actually changes a lot because suddenly we can look at individual differences as they play out in everyday behavior. And the question is, how can we possibly use this information ethically? The University of Notre Dame is testing an algorithm that collects screenshots of patients' online activity to flag the use or viewing of terms related to suicide and self-harm. By pairing that data with EMAs, ecological momentary assessments, and psychological metrics from smartwatches, they hope to build a tool that can alert clinicians in real time about patients' suicide risk. And of course, if somebody knows that this is happening, they are not going to do any of this stuff. It looks like a good idea now, but it's so intrusive. And there are the 4 magazines that I was just talking about. So there you go. That's my lecture on artificial intelligence. I'm sorry I didn't say anything too positive about artificial intelligence. You know, Siri helps. It can help you around the house. The problem is, of course, who is getting all of this information? That's the question I think that we all need to ask before we buy into all of this stuff. So next week we'll start talking about video games and some of the problems with video game addiction.